Here are the notes for 1.5. Inductive reasoning can be best shown by an inverted triangle. And what that is showing us is that we take many examples and we draw a conclusion or rule from them. So we put everything into our machine, we look for patterns, and we draw the conclusion out. Now, deductive reasoning is exactly the opposite. Here, we take the conclusion or the rule and we apply it to many situations. And so in this case, we start here and we go down like this. So you take the distributive formula and you apply it to 30 problems using it. Now a conjunction is two statements joined with and. Both must be true. For the whole statement to be true. A disjunction is two statements joined with or, excuse me. One, the other, or both can be true. For the whole statement to be true. So for example, if mom says to clean your room and take out the trash before you go out on Friday, and you only clean your room, you don't get to go out because she used and. Both have to be true. But if she said clean your room or take out the trash and you can go out, as long as you do one of the tasks, you can go out. Now this next picture is a Venn diagram, usually used to do compare and contrast and to show similarities, but it also works in math. And this little area right here represents our conjunction. This is our and, where two sets of criteria are true. So if we made this our student body, and we made this 10th graders, and we made this athletes, a student who is right here would have to be a 10th grader and an athlete. Over here, they would be a 10th grader, but not an athlete. And over here, they would be a 9th, 11th, or 12th grade athlete. And out here would be a non-athlete, non-10th grader. So we are going to form some conjunctions and some disjunctions using two statements. It's as simple as joining them with the appropriate word. In a conjunction, we use and. So pi is a rational number, and 4 is a factor of 30. Now when I look at this, pi is a rational number. That's true. Rational numbers are numbers that can be expressed as fractions. 4 is a factor of 30 is false, so this whole statement is false. But when I write it as a disjunction, pi is a rational number, or 4 is a factor of 12, or factor of 30, excuse me. In this case, this is still true, this is still false, but the whole statement is true because disjunctions say one, the other, or both to be true. Now, conditionals are if-then statements. We see a lot of these in our theorems. If a pair of angles are vertical angles, then they are equal. You have to have the first criteria in order to get the second. So the hypothesis is the if part. The conclusion is the then part. When we are working with any of these statements, we are going to be aware of keywords. And those keywords are all, every, some, and none. And we take them quite literally. If I say all students something, it means every single one. If I say some students, then that leaves room for some to be the criteria and some not to be the criteria. This box right here is just showing you the different ways that you can write conditionals. P implies Q. If P, then Q. With the arrow notation is probably the most common, as is if P, then Q. But we could also say every P is a Q, P implies Q, P only if Q. Now, counterexamples come in very handy. This is how you prove a conditional false. It's one example where conditional is false. And that is all you need to prove it false. I call them the yeah, but. It's a lot easier to prove things false than it is to prove things true. Now, a converse, you're going to switch the if and then in a conditional. It is true or false on its own. So no matter what happens with the conditional, you still have to look at the converse separately to see if it is true or false. Now, example, the sum of the measures of a rectangle is 360. Whatever follows the verb becomes the then part in your original statement. And sometimes you have to insert kind of a placeholder noun to make your if-then statement sound good. So we would say if a figure is a rectangle, then the angle sum is 360. Now, then we decide what is the hypothesis. That is that the figure is a rectangle. The conclusion, the sum equals 360. Now, is this true or false? So to decide true or false, you hold the hypothesis true and see if any other conclusion works. So if I have a rectangle, can I have any other sum except 360? No. So that one's true. Now when I write the converse, I will write if the sum equals 360, then figure is a rectangle. Now if I look for true or false here, if I hold if the sum is 360, does it have to be a rectangle? The answer is no. My counterexample, I could have a circle. The sum of a circle is 360. I could have a trapezoid, which is not a rectangle but also has 360. And you just need one counterexample. Now lastly, we're going to write the implications in if-then. True or false, write the converse, true or false. Every number divisible by 5 ends in 0. So if a number is divisible by 5, then it ends in 0. The converse, if a number ends in 0, then divisible by 5. Now, are these true or false? So if a number is divisible by 5, does it have to end in 0? No, that's false. It could end with 5. So you could either write end with 5 or you could put 55 as your counterexample. So if a number ends in 0, does it have to be divisible by 5? That is true. 5 will always go into a number that ends in 0. Notice it's not saying that 5 is the only factor. It's just saying that 5 will always go into it. Now the last one, if an animal, if a cat, if an animal is a cat, then it has 4 feet. The converse of that, if an animal has 4 feet, then it is a cat. Now we're going to go back and decide true or false. If an animal is a cat, does it have to have 4 feet? That is true. If an animal has 4 feet, does it have to be a cat? And that, of course, is a false. It could be a dog. It could be a raccoon. It could be any other 4-footed animal. That is not a cat.